Hi, this is a microprocessor constructed in a cellular automaton that computes the Fibonacci numbers and outputs them in base 10. On the left is the index of the currently executing instruction, and at the top is the output of Fibonacci. 256 generations of the automaton are simulated each frame at 60 frames per second, and each instruction takes 2,880 generations to execute, so the processor is currently running at about 5 Hz. Let's increase the speed to around 85 Hz. It will stop after reaching the largest Fibonacci number that can fit within 2 bytes, which is around 46,000. So how does it work? This automaton, which I've called DECA, or Digital Electronic Cellular Automaton, has 7 states: background, which is black, signal head, which is white, signal tail, which is purple, wire, which is a dark gray, and red, green, and yellow, which are each used for multiple purposes. My automaton is defined using a language called Nutshell, which transpiles to Gali's native rule table format. Each of these lines represents one transition which cells can undergo. Together, this describes the entire rule. Let's start with the white, purple, and gray states. I've made the gray slightly brighter so that it's easier to see. A signal, composed of one white cell and one purple cell, will move along a wire made of gray cells. Each gray cell, if it has exactly one white neighbor, will become white, and each white cell will always turn to purple, and each purple cell turns back to gray. If a signal comes to a fork, it will split, and if 2 signals meet, they will annihilate. Since the state of each cell is based only on its 4 immediate neighbors, diagonal wires are not possible. Red and green cells act as diodes. Green cells will only allow signals coming from a diagonally adjacent cell, while red signals will only allow signals coming from an orthogonally opposite cell. As a signal passes a red or green cell, the cell will briefly toggle between red and green. You see, these blocked the signal, but these allowed it. A red or green cell will never block a signal at a dead end. We can use these to construct logic gates. For example, here is an AND gate which resembles a transistor. If both signals are present, this one is allowed to pass through. However, if this signal is absent, the signal will die. Or if this signal is absent, there will be nothing at the output. And if neither signal is there, of course nothing happens. Changing the red cell to a green one produces an AND NOT gate. Only if the lower signal is present, but the left signal is not present, will we get an output at the top. There we get no output. Here we do get an output. If red or green signals appear in a pair, they will not change state when a signal passes by. This can be used to create permanent diodes. A yellow cell at the end of a wire will create a constant stream of signals, with 2 blank spaces between them. The presence of a nearby yellow cell will alter the behavior of a red or green cell. This construction serves as a toggleable signal source. A pattern like this creates a crossover. A crossover will block signals coming from the other direction, so it only has 2 inputs and 2 outputs. The yellow state's usage in a crossover is completely distinct from its usage as a source of signals. Here is a collection of logic gates based on the functions I've demonstrated. Note that timing is very important. If signals arrive out of sync, the logic gates will not work. This circuit adds 1 to a binary number. This signal marks the start of the number, and the signals along here represent the bits of the number, with the least significant bit first. The signal on the right is just for reference of where the output begins. The carry is stored in this block of cells here, which forms a 2x2 loop. The carry continues only if the next bit of the input is a 1. Otherwise, it dies. The current state of the carry is XORed with the next bit of the input to produce the next bit of the output. Our input was the binary representation of the number 29, and our output is the binary representation of the number 30. The incrementer is essentially a half adder. Here is the AND gate, and here is the XOR gate. Exchanging the AND gate for an AND NOT gate produces a decrementer. Here is a full adder based on the same principles. Using a crossover, AND gate, and AND NOT gate, we can produce a demultiplexer. This is the data input, and this is the selector. If the selector is 1, the data will go to the top output. If the selector is 0, the data will go to the bottom output. If the data is 0, no signal will appear at either output. This is the same logic in a slightly more useful form for the final design. The selector input travels through the top unaltered, so this can be used to chain demultiplexers. This is the memory cell used in the processor's ROM. This loop can hold 18 signals. Each signal is 1 bit. When a signal arrives at the read input, 1 bit is read from the loop and sent to the data output. Notice that this device can be tiled both horizontally and vertically. The read input will pass through from left to right, and the data output will pass through from bottom to top. The read input must be synchronized to a multiple of 72, because the total period of the loop is 72 generations. This is the ROM used in the final design. If you're watching this full screen on a 1080p display, each pixel is 1 cell. The ROM can hold up to 1024 instructions, each of which is 18 bits long. At the bottom left is the input. On the right is the clock input. On the left is the address, which is 10 bits long. This leads into a serial to parallel converter, which uses a combination of delays, crossovers, and AND gates to send each bit of the address down a different line. The clock signal and each bit of the address is then duplicated 18-fold, once for each bit of the instruction. This section and this section are just long delays to synchronize the bits so that they arrive at the right relative timing to the demultiplexers. These, along the side and top of the ROM, are the demultiplexers, which select the row and column of the desired instruction. Here is the currently selected instruction. The read signal arriving from the vertical demux on the left reads all 18 bits of each instruction in its row. These signals then travel upwards, where the horizontal demux selects one of the columns. Here it's filtering out the others and selecting the one we want. This is the 18-bit output of the instruction at the specified address. The registers follow a similar principle. This loop contains the 8 bits stored in the register, and a signal traveling along the select line will send one of them to the data output. Writing is a little bit more complicated. This line is the write signal, and this line is the data to write. The select signal here is ANDed with the write signal. This is then fed into an AND NOT gate, which deletes the signals already in the loop. Same signal is sent along here into an AND gate with the data to be written, so the data only enters the register that has been selected. The addressing for the registers is similar to the ROM. Here is the serial to parallel converter, and here are duplicators for the signals. Same thing for the write. This is just delay, and so is this little squiggly bit. Here are the demultiplexers, This is some stuff for fixing the output of the device, since when the read signal comes in, it actually reads the upper bits of the register and then the lower bits. But everything in this processor is middle endian, so we have to correct this at the output using some OR gates and clever delays. This is the 7-segment display. At the bottom is just a loop with an incrementer to display the different digits. On the left here is a more compact demultiplexer, which unfortunately I only developed after completing both the registers and the ROM. This is a lookup table. Each section here is 1 bit, each row is 1 digit. This green or red cell denotes the actual value of the segment for that digit. These are set-reset memory cells. If a signal comes along this line, it will set. If a signal comes along this line, it will reset. This is a bunch of delay and crossovers so that the segments, the lines here, correspond to the segments A, B, C, D, E, F, and G on a regular 7-segment display. And the delay is to make the segments appear to update roughly in sync. The segments themselves are just wires which, when signals flow through them, appear to light up. By now you should recognize most of the major components of the processor. The ROM is here, the registers are here, and the 7-segment displays are all the same. This delay here is so that each display will show a different part of the data signal going through. Here, the instruction is red. These are the 5 jump instructions. As the instruction comes down here and the clock signal arrives here, it will go up through only if the instruction bits exactly match the pattern of green and red. For the conditional jumps, they read the carry and 0 flags, which are stored in set-reset memory latches, like the ones shown in the 7-segment display. If it is a jump instruction and the condition is true, then one signal will be sent along this jump line, and the new address will be sent along the address line. This is combined with an incremented address, and one of them is selected using this demuffs here. Most of the long squiggly bits are just delays to synchronize signals. AND, OR, XOR, and load instructions, or addition and subtraction instructions, will trigger a signal to go along this line here. This line travels up through here, goes through some delay, and eventually comes through here, where another set of decoding happens to determine exactly which instruction it is, and which logic gate it should go through. The load simply takes one argument directly, and AND's 2 arguments, or OR's 2 arguments, etc. Subtraction is done by negating one input here, and negating the carry over here, using an XOR. An output instruction will send a signal down this line, along with a clock signal to update the 7-segment displays. This part here extracts the arguments from an instruction. X and Y, which are the addresses of registers, each of which, there are 16 registers, so the address for a register is 4 bits, or K, which is an 8-bit constant to be used instead of the value of one of the registers. A is the address to jump to. A is 12 bits, K is 8 bits, X and Y are each 4 bits. So these devices generate 4, 8, and 12-bit sequences, respectively, to extract that bit from the instruction. X and Y are sent up to the registers, where they're sent along this data line. The clock signal will extract Y along this line, and X along this line. K, sent directly here, up this line, and demultiplexed with Y, depending on whether the instruction calls for it, which is detected right here. So that should give you a reasonably good idea of how this whole thing works. But how do you actually program it? First, the code must be written in Picoblaze assembly, using the subset of instructions that have been implemented. This is the Fibonacci code, which uses subtraction to do the division by 10 necessary for binary to BCD conversion, since there are no bit shifts. First, the assembly program must be compiled using a program called automaton. Once the .mem file has been generated, this can be converted into a ROM using this Python script, which creates a run-length encoded ROM pattern. This is copied to the clipboard and can be pasted so that the yellow pluses line up into the ROM. And that's about it.